All right, so this is 17.5, divergence and curl. And what we're going to talk about here is extending the concept of divergence and curl from 17.4 to 3 dimensions. And in the next section, we'll start using these guys. Next few sections, we'll start using these guys. So this is just going to be, this section is entirely just going to be an introduction to these two concepts. All right, so F is a vector field. We're in 3 dimensions now. Let's call it P, Q, and R. And again, our book likes to use F, G, and H, but I'm just going to go with P, Q, and R. These are all functions of 3 variables. Let's just get right into it. So divergence of F. So this is going to be very, very similar to essentially a completely natural extension to the divergence theorem in 2 dimensions. It's just going to be dp dx. So the first guy dx, second one dy, dq dy, third one dz. All right, and now you can imagine what the divergence of a vector field in 4 dimensions, 5 dimensions, and so on should be, and you would be correct. All right. Okay, as with the previous section in the plane, the divergence of vector field in space is a function. All right, so this is no longer a vector field; it's now a function. Okay. Let's write down a curl, and then we'll talk about a couple bits of notation for each of these guys. So the curl of F is going to be, well, a little more complicated. And the way most people learn to compute this is you go I, J, K. So we're going to do essentially what we did last time to introduce the curl. But ultimately last time in the Green's function section, the curl was a function, but this time it's actually going to be a legitimate vector field. So ijk, and then we're going to put ddx here, just like what we did in 2 dimensions, ddy, ddz. But this time we're actually going to have stuff to differentiate p, q, and r. All right. So ultimately, if you calculate this, this is going to be, let's actually do it. So here and here. So the I component of the curl is going to be dr, dr dy minus dq dz. This is the I component, right? And then we've got the j component, cross out that and that, and again, minus the j component. So this is dr dx minus dp dz, j, and then the k component is going to be dq dx minus dp dy. All right. Okay. So curl of F is a vector field, not a function. So in the two variable case in the plane, we thought of it as a function just because in a way it was always in the k direction. So it really, the direction didn't really tell us too much. Here, the direction actually matters quite a bit. All right, so this is in a way the correct way to think of the curl. So something interesting here, while the divergence, you can extend it to any dimensions as extremely naturally, right? For sure, you figured out how to do it already. The curl, how would you extend that to higher dimensions? You can't. All right, so the curl is restricted to a 3-dimensional setting. And you can kind of see it in the way we compute it. When we compute it with this kind of determinant procedure, right? The first row goes towards the the ijk, right? So if you had, let's say 4 dimensions, you would have an ijk and then one more entry here, right? Well, the second one goes for the second entries go in the second entry go the partials, right? So partial x, partial y, partial z, maybe partial w if you added one more. The third one goes the vector field, so PQR, and then maybe, if there's 4 dimensions, add one more. But if you just had that, you can't take a determinant. It's not a square matrix, right? So you would need one more row. But we don't have one more. We don't at least have a natural, easy way to define one more row, right? So the curl is naturally, at least the way we've defined it, it's a naturally 3-dimensional thing that doesn't exist outside of 3 dimensions and 2 dimensions, of course. Okay, so that alone makes it somewhat interesting, and perhaps at the very, very end of the class we'll talk about how all these things tie together in one bundle. Okay, now first of all, I like the notation div and curl like that, just written out. But there's some other notation that's very commonly used. In fact, probably much more common than my notation here, or than not in my notation, but the notation that I use. So divergence f is often written as the gradient symbol and then dot the vector field. Okay, this is purely notational. You're not actually taking this symbol and dotting it with anything. But in a way, this is kind of nice notation because what is the divergence? It was dp dx plus dq dy plus dr dz, right? So if you think about this notation on the right-hand side, writing it kind of in a vector notation, this would be like ddx, comma ddy, comma ddz, and then dot with pqr, right? And anytime you have a dd whatever interacting with a function, you just take the derivative, right? So dp dx, dq dy, dr dz. Okay, so in that, if you think about it in this way, this notation is really nice in that it helps you remember what the divergence is. Okay, so super common, especially in physics classes. All right. In the same way, if we look at the definition of the curl, right, here we have ijk. When we normally take the cross product of two vectors, you go ijk, vector 1 in the second row, and then vector 2 in the third row, right? And that would be the two vectors crossed together. So the curl, alternatively, can be written as the same kind of the gradient symbol or the del symbol, or the nabla symbol is often called, and then cross f, right? So again, when you do have something A cross B, right, usually you write A in the second row, B in the third row, and so that's kind of what we're doing here, all right? So this del cross f, super common, and again, especially common in like physics classes, all right? So you should definitely kind of make sure you're okay with this notation. And again, it's really good because it kind of helps you remember the formulas for these guys. Okay, what do these guys mean? So we talked about the meaning of the divergence and the curl in the last section. We basically used Green's theorem to kind of see the meaning. The divergence is the infinitesimal flow out of your point. And the curl is the infinitesimal rotation at your point, right? In 3 dimensions, same idea. So the divergence is literally exactly the same idea. You have a point, it's measuring how much stuff is coming out of that point. Of course, as always, net, right? So if stuff is going in and then stuff is coming out, you're counting the stuff going in as negative and the stuff coming out as positive. Okay. Okay, except now, of course, we're in 3 dimensions. So this particular picture here would look like divergence f bigger than 0, right? Something like that. Okay, and again, this is an infinitesimal idea. It's kind of what's happening at this point in a way, right? And remember, we called this this picture here a source because things are coming out of it, right? And then if it was the other direction, divergence f less than 0, which again, the kind of stereotypical picture would be like that, divergence f would be less than 0. Okay, but again, remember the pictures do not have to necessarily look like that. Exactly this for sources and sinks. You have the other kind of picture where you have perhaps large vectors coming in, but smaller vectors coming out in a way, right? And so overall, more things is coming in than going out, and so the divergence is less than 0 here. Right? So literally the same ideas as in the two variable case. All right, more interesting, maybe more interesting, but at least different. At least this is interesting in that it's different. The curl is now a vector, vector field, and so the curl at each point is now a vector, right? Compared to the planar case. So what does that mean? Well, the direction of the curl. So let's say we're at a point right here, and we're looking at the curl of f, and it happens to be this vector right here. Right? This is again in space. So if this is the direction for the curl, then what that means is if or essentially things are your vector field is flowing rotationally around this point in a plane perpendicular to the curl vector. All right. So you can think of your vector field as rotating in this direction, like that. All right. Perhaps a more precise way to say it would be if this is that vector. If I put kind of paddles like this, right, or like a pinwheel or something like this, in the plane that's perpendicular again to the direction of the curl, then it's going to spin first of all counterclockwise in this direction. So always when I say counterclockwise, when what we're doing is we're looking from above. So our eye is up here. We're looking downwards towards the head of the vector like this, and what we would see is flow counterclockwise in that way. All right, you have to make this distinction because if you're looking from underneath, then it would be clockwise instead. Right, so you want to be slightly careful about this. So the book is actually quite sloppy in this, especially in the next section. You should always be very careful about saying what direction if you're going to say counterclockwise or clockwise, you should always say what direction you're looking from. All right. Okay, so something like counterclockwise when viewed from above or something like that. All right. That is, of course, assuming that the word above makes sense. Okay, because it wouldn't if you had a plane like the YZ plane. There's no above in terms of the YZ plane, right? Or at least no colloquial concept of above when you're talking about the YZ plane. What's above the YZ plane? Doesn't make sense, right? But you can say above the XY plane. That makes sense. You can say above the plane x plus y plus z equals 10. That makes sense because you'd be talking about looking from, in a way, the positive z direction, right? From the positive z axis downwards. Okay. All right. In any case, so if you put these paddles in this configuration, this is where the paddles would kind of spin the fastest. All right. So that's the kind of meaning of the direction of the curl. The length of the curl would be, in a way, telling you how fast these paddles would spin. All right. How rotational is the vector field around this point? All right. And again, this is all at a point, so this is all infinitesimal. So obviously, if you actually built a paddle like this, it might not do the exact behavior because these paddles are quite a bit of ways away from your point, right? So it may not, the actual physical object that you create might not reflect the behavior at that point, right? You would actually have to make smaller and smaller paddles and then take a limit. Okay, but the core idea is the same from the planar case. The divergence is source or sink, same idea, and the curl is rotation. Same idea, but a little more complex. Okay. So, so in fact, from this description of the curl, you can kind of imagine that um, it's not necessarily so easy to define the curl as a vector field if you had 4 dimensions, right? Because if you had 4 dimensions, the direction of the curl, let's say, is this direction, but everything perpendicular to it is 3 dimensional, right? So it's really hard to talk about rotation around something when you're in when you're talking about an entire space. Whereas in 2 dimensional, right, the concept of around, if I have only 2 dimensions, the concept of going around this point makes perfect sense. Okay, a couple technical details. These things are essentially derivatives, right? So these are derivatives, right, of f. And that's how we thought of them last time when we talked about Green's theorem, right? One side of the Green's theorem is derivatives of f. The other side is no derivatives of f, but on the boundary, right? So you should think of these as in a way, two different derivatives of f, or two different ways to differentiate a vector field. And being a derivative of a vector field, or being a derivative, means that you probably should satisfy properties that derivatives satisfy, right? So for example, and the answer is yes, they do satisfy exactly those properties. So for example, divergence of f plus g, if I have two vector fields and I add them together, right, that's the same as divergence of f plus divergence of g. Okay. Same with the curl. You have the curl f plus g is equal to curl of f. And you can check this just straight from the definition. Literally nothing fancy going on here. Let's see, divergence of, so these are, if you have two functions in one variable calculus, the derivative of f plus g is f prime plus g prime, right? So basically, these mirror, the same properties are mirrored with both the divergence and the curl. So divergence of, let's say, a constant times f, right? If you modify your vector field just by a constant 10, right? Then you could just pull that constant out. And again, this comes directly from the fact that in one variable calculus this works, and then just using the definition of both the divergence and the curl. So curl CF is equal to C curl F. All right. Let's see. Another super important feature of derivatives is the product rule, right? And so you might ask the question, what is, for example, the divergence of, let's say, a function? So instead of a constant, this is a function times f, right? So first of all, this concept makes sense because what we're talking about is f of x, y. At any point, this looks like this, right? Capital F. Let me write capital F as P of x, y, z, Q of x, y, z, and R of x, y, z, right? So at each particular point x, y, z, this f times capital F is just f of x, y, z times p of x, y, z, f of x, y, z times q of x, y, z, and so on. All right, so it makes perfect sense to multiply a function to a vector field. All right. Okay, so the divergence of this is going to be very much like the divergence, very much like the product rule. So this is going to turn out to be gradient of f dot capital F, and then plus f times the divergence of capital F. All right. And why is this true? You can just write it out. Just use this expression right here, take the divergence of it, and you'll see literally this pop out. All right. So this is the product rule because you're taking in a way the derivative of the product of two things, and what you end up with is the derivative of the first thing times, in a way, the dot product, the derivative of the second thing, and then plus the first thing times the derivative of the second thing. All right. So in a way, the product rule is satisfied, right? Notice I did the divergence of a function times a vector field. You can't do the divergence of, for example, f times g, because there's no such thing as f times g, right? But you can think about divergence of f dot g, right? You cannot think about the divergence of f dot g either, because f dot g is a function, right? And you can't have the divergence of a function. The divergence is something that operates on or acts on vector fields, right? So this is not allowed. Okay. Whereas this guy up here is perfectly legal. Okay. So now you might ask, what's the divergence of f cross g? Right? So this makes sense because f cross g is a vector. If f is a vector field and g is a vector field, then f cross g is a vector field, and you're allowed to take the divergence of that. Right? So probably maybe a good exercise for you is make a hypothesis as to what this guy should be, and then compute it, right? Where maybe you call f p, q, and r, right? And you call g s, t, and u, right? And then you confirm it, or you check your hypothesis. Okay. All right. So roughly, there's in a way a few ways to do the product rule, and essentially they all work. And what I mean by essentially is, of course, you have to think of it in the right way, right? So, for example, curl of f, what did I use up there? ff, okay, of a function times my vector field. So again, this makes sense because the inside is a vector field. You can take the curl of a vector field. If you just brutally calculate this, this is going to be f curl capital F, and then plus gradient f, gradient little f, cross capital F. All right. So things might not look literally like the product rule, but again, essentially you have the right properties, right? So this is f, and then the derivative of the other term, and then this is the other term, the derivative of the first term. Okay. All right, so you can play around with what other things might make sense, and you might try to calculate what they are. Okay. So one thing to notice about the curl, we noticed last time that in 2 dimensions in the plane, the curl was, when you take the curl of a function, if that was 0, then you're conservative, right? Or that's the condition for being conservative in a simply connected domain, right? So now, same idea. So conservative tells you curl is 0. Let's write f conservative tells you curl of f is equal to 0. All right. And if curl of f is 0, and you're in a simply connected domain, then you're conservative. All right. Nothing new here. If you just look at the our conditions for being conservative in I think it was 17.2 sections ago, then you'll see exactly that the entries of the curl have to be 0. All right. So nothing new, but again, it's something that does make intuitive sense when you think about what the curl means, because for the curl to be non-zero means your vector field does have some sort of rotational aspect at that point where it's non-zero, right? But if your vector field has a rotational aspect to it, then it can't be the gradient of something, because gradients can't have rotational aspects. Because if they did, then when you integrate around a circle, you come back to a different value for your potential. All right. So this makes perfect sense when you think about it kind of in a intuitive or physics manner. Okay. Um, let's see. So combinations. So we by now at this point we have kind of three types of derivatives um, that we can do that involve vector fields in some way, right? We can do the gradient, right, of a function, and that ends up being a vector field, right? We can do the divergence, right? That's a derivative in a way of a vector field, and you get a function. And then we can take the curl, which is kind of a derivative of a vector field, and you end up with a vector field again, right? So one question you can ask is how these three interact with each other. So let's write down a few of these interactions. Maybe before I write them down, maybe one thing you could do yourself is to first of all just write down or think about which of these combinations are actually legal, right? What I mean by combinations is one after the other. So is it allowed for me to take the gradient of a function and then take the divergence of that? Is it allowed for me to take the gradient of a function and take the curl of that? Is it allowed to take the divergence of a vector field and then take the curl of that? Right? That would be illegal because divergence is a function. You can't take curl of a function. So an example like that. So maybe go through them all, see which ones are legal. All right. And then for the ones that are legal, see if you can recognize any special properties about that combination, because several of them do have special properties. So maybe a good idea to pause now and just try them out yourself. And then let me actually talk about it right now. So, all right. So let's start with gradients. So gradient of. So we can't take the gradient of a gradient, right? Because if f is a function, the gradient of f is a vector field, and you can't take the gradient of a vector field, right? You can only take gradient of functions. The second one is gradient of a divergence. That one's legal because divergence of f is a function, and you're allowed to take the gradient of a function, right? So this guy is legal. What is it equal to? Does it have a special identity or anything related to it? No, right? So that's a little anticlimactic, but it is a legal quantity, all right? Can you take the gradient of a curl? No, because the curl of a vector field is a vector field. You can't take the gradient of a vector field, all right? Okay, next, let's talk about the divergence. So the divergence of a gradient. Can you do that? Yes. Divergence of a gradient is legal because the gradient of a function is a vector field, and you're allowed to take the divergence of a vector field. Okay? And in fact, when you do this, you start with a function. After you do the gradient, you have a vector field. After you take the divergence, you have a function again. All right? So this guy is a function. And in fact, if you write it out, this is going to be in 3 dimensions. This is going to be d squared f dx squared plus d squared f dy squared plus d squared f dz squared. Oops, plus. And in 2 dimensions, you wouldn't have the z term. In 4 dimensions, you would add a term. 5 dimensions, you would add another term, and so on. All right? If you just write out what the meaning of gradient f is and you write out what the meaning of divergence is, this is literally what you get. So nothing fancy happened here. Now, there's no kind of really nice identity that exists here, but this guy is actually a super important quantity, and it's so important it has a name. It's called a Laplacian. All right. if you've seen, any kind of mathematical physics class and done waves, right, you'll definitely have worked with the Laplacian, f double prime, essentially, right? In one dimensions, if you get rid of the y and the z, it's essentially d squared f dx squared, right? So that would be the one-dimensional version of this. The two-dimensional version, so in one dimension, when you look at f prime prime, um, let's say in the context of waves, right? So you would be solving something like f prime prime f lambda f equals 0, right? You're talking about sines and cosine waves, right? So those would be like you pluck a guitar string, right? And the guitar string vibrates up and down. The waves are solutions to this guy, or made up of sums of solutions of this guy, all right? If you go to two dimensions, you could still make the analogy. You'd be looking at Laplacian f plus lambda f. You'd be solving these guys. And this, what would this be? This would be a drum. You hit the drum surface vibrates, the skin vibrates up and down. How does it vibrate? Sums of solutions of this guy here. All right. If you've seen the kind of physics experiment where you put sand on a flat surface and then you kind of you vibrate that surface, and then the sand moves to certain locations. So maybe you'll see something like this, and then when you shake the surface kind of with a constant frequency, you'll see that all the sand moves to specific areas. All right, and then there's big gaps in between. That's essentially showing you solutions to this guy here. All right. Okay. So it models, in a way, the sound of drums, or at least you can think of it that way. So this is super important. In fact, you've seen it on homework problems as well. Laplacians come out of examinations of energies, right? Like this. You could do this. I guess in the homework we did it with f prime squared, but the kind of higher dimensional version would be this guy right there. And if you do an optimization problem where you're minimizing something like this quantity, perhaps with a constraint, right? Exactly like how we talked about in the extra credit problem. If you do it, if you minimize this, whether with a constraint or without a constraint, and you look at the directional derivatives and you say, what happens at the minimum, what you'll get is instead of like in our class in multivariable calculus, instead of getting an algebra problem, right, for finding the critical points, you get a differential equation, and that differential equation looks something like that. All right. So super important in that things like this are often called energies, right? And you want to minimize energies oftentimes in physics. All right, or action or something like that. All right, so this while this divergence of the gradient doesn't have a nice kind of identity associated with it, it's a super important operator. Okay, let's see. Can we take the divergence of a curl? Yes, we can, right? Curl of a vector field is itself a vector field, and the divergence works on vector fields, right? So you can take the divergence of a vector field. So this guy is perfectly legal, but compared to the Laplacian, this is not as interesting because this guy's always zero, all right? It's always the zero function. Why is it? Just write it out. Literally write out what the curl means, curl of f means, and then write out what the divergence of that is, and you get zero. All right. By the way, there is deeper meaning behind all three of these guys, divergence, curl, and the gradient. They're all unified by one operation in a way. But we never talk about this in multivariable calculus. Maybe I'll talk about it at the very end of class. So for now, it looks like some of these things are really strange. Some of these interactions are strange. Why is this one in particular zero, whereas the previous one, divergence of the gradient, why is that not zero? it can all be explained through this unifying idea, again, that we're not going to go through today. All right, but again, this one here is 0. No surprise at all, just if you just write out the definition. Okay, and then finally, the curl. So we can, oh, by the way, you can't take the divergence of the divergence, because divergence of f is a function. You can't take the divergence of a function. All right, what about the curl? So the curl of a function, sorry, curl of a gradient. Can we do that? Yes, right? Because the gradient of a function is a vector field, and curls act on vector fields. Right? So this guy is perfectly legal, but again, it's not interesting because it's always 0. Why is that? Well, again, if you just write it out, you'll see that 0. But we also know that it should be 0 because we just said a few minutes ago that the curl of a conservative vector field is always 0, right? Because a conservative vector field is irrotational. It's not rotational. And again, a conservative vector field is not rotational because, well, gradient f cannot have rotations, or else it can't be a nicely defined function. All right. So this one, again, you can just write it out. It's obviously true when you just write out the definitions of the curl and the gradient. But I'm going to write it because conservative. Let me write it like this. Gradient f conservative. All right. By the way, for this above one, you can think of this as, in words, you can think of this as the curl of a vector field has no sources or sinks, right? Because that's what divergence measures. Okay. All right. You can't take the curl of a divergence because divergence is a function. You can't take the curl of a function. And the last one would be you can take the curl of a curl, right? But that one's not interesting at all. All right. Okay. So these three in the middle are particularly interesting. This one here, just because of the application. Sorry, where is it? Here. This one here, and that one there. All right. Okay. Finally, let's write out if f is conservative, right? In other words, f is equal to the gradient of some potential function. Then this tells you have path independence, right? It tells you integrals, line integrals. I should write that down. Line integrals in loops is equal to 0, right? And that's essentially the same as path independence. It is the same as path independence. And then now we can also say that the curl is 0. All right. Okay, and all of these guys are actually equivalent if you're in a simply connected region. And it's definitely not true if you're not in a simply connected region. All right. So just like in the paper homework from last week, where there was a vector field that was whose curl was 0. Actually, we didn't use the word curl, right? There was a vector field where the criterion dp sorry, I guess we use g and f and g. dg x is equal to df dy, but the vector field was not conservative. The same thing can happen in higher dimensions. All right. In that example on the paper homework, it was because the vector field was essentially a rotational vector field, and the condition of being simply connected didn't hold because it wasn't defined there. So no matter what, your region is not a simply connected region, right? By the way, if we consider just this region here, then it would be conservative. All right. All right. So in the three-dimensional case, you can make pretty much the same example. For you create a simply, you could do like a rotational, kind of a cheating example, but you do the same vector field that's kind of rotating around, except you make it rotate around the z-axis. So at this height, it would rotate around the z-axis at that height. At this height, it would rotate around the z-axis at that height. So it kind of has no z component. And so what happens is you have this hole, which is the z-axis. And so it's not simply connected because you have this curve right there that can't be shrunken to just a point. All right. So in that situation, you could have vector field. You could have a vector field, that one, the one that I just drew, whose curl is 0, but which is not conservative. Okay. And again, all of this, we're spending a lot of time using talking about the word conservative vector field. And again, that's because, these things are just super important, especially in physics. Okay. All right. So this section was basically just an introduction to the divergence and the curl in higher dimensions, or in dimension 3, the divergence in higher dimensions, but not the curl. So what we'll do in the next sections is we're going to try to use them. We're not quite ready to use them yet because we need to understand how to integrate over surfaces. So for example, integrating over let's say the upper hemisphere, right, of a sphere. So just this upper hemisphere here. All right, so we want to be able to integrate over that. And then what we'll do is, once we understand that, we'll have a version of Green's theorem, except for integration over surfaces. That'll be called Stokes' theorem. And so we saw that Green's theorem, there was a version, the circulation version involved a curl. So that's where we're going to use our new version of the curl, the three-dimensional version of the curl, is going to come in when we integrate over surfaces, right? So next section is integral over surfaces. The section after that is where we actually put together this section, divergence and curl, with integration over surfaces, all right? And then the last section of the class is going to be what's called the divergence theorem, and that's an extension of, in a way, the Green's theorem, the flux version. And the context we'll be looking at it in is you're integrating the inside of a sphere, right? So rho equals 0 to r, right? And then d phi, the d phi and d thetas are 0 to pi and 0 to 2 pi. So the inside of a sphere. That's going to be the integral of the divergence of a function of a vector field inside a sphere is going to be equal to the vector field on the boundary, something to do with the vector field on the boundary of the sphere, which would be just the sphere, all right? The surface of the sphere as opposed to the ball, the inside of the sphere, all right? So we'll be using both of these guys in our next two big theorems, starting 2 sections from now.